Okay. Hi, everybody. So good afternoon. Welcome to Machine Learning for Materials Science. Um, a few logistical things that I wanted to clarify. Those who are eyeing for a credit in this course, you definitely have to participate in the project and the exam. For the project, I have told there is a due on 5th of September. uh, like the first step is due, so you have to basically create a video of less than 5 minutes, explaining your problem, giving some timelines on what you aim to achieve by the midterm and what you aim to achieve by the end term. These are of course subject to change, and if any base paper that you have that you would like to follow, uh, so those you can give. And generally, the expectation, just to make sure everything is clear, by the midterm, it is expected that you plan to do everything that is there in the base paper, or you have covered or ran some generic experiments and set up the data set, which you can just do some basic stuff. There is nothing new that is has been added by you. Yeah. Those basic stuffs can be added in the midterm, and in the end term, from midterm to end term, you're trying something a bit newer, like so changing this, changing that, or putting some of your domain knowledge that you have gathered into the pipeline. Yeah. That's the basically use case, and that's what we want from this entire process. So September 5th is the deadline to submit. I will confirm how you're going to submit in the next class on the Wednesday. Hmm. I'm trying something. If it works out, fine. Yeah. And for please try to have a partner in this, and you can interact with yourselves over. If some of you are on YouTube chats, you can ask someone to be your partner and just be okay, and then probably write an email to each other. And those who are on WebEx, same principle. If you don't have a partner in your particular institute, yes, it's good to have a partner who does not work, right? You can blame him or her. Fine. So with that, we will go ahead and start. We will. So today's. So just to give a repeat, AI is done, ML is done, YML is done, some of the maths through ML is done. We then looked at the way I told you that we'll be looking at five fundamental supervised algorithms. We have looked at linear regression, logistic regression, yeah, and decision trees. We also looked at the gradient descent, which is used to optimize various parameters in the models that we have built. Yes. And the last class we did decision trees, and specifically we ended with two questions, which I am hoping to get some answers from you. Please feel free to type in the chat. Those who are on YouTube, I'm really sorry, I'll not be able to look through. And the first question that I had asked was basically, if you remember the decision tree graph, that looked like very straight cuts across X or across Y that are parallel to one of the axes, right? So how can we have, let's say, diagonal cuts? Sometimes we might require diagonal cuts, right? So how do we have it? Hmm. Before you continue to type, if you have some answers in your mind, uh, the general principle is like the whatever the sklearn provides or whatever the general algorithms. So like the one that we use is, let's say, Gini impurity, and that is most likely called cart in sklearn, and we can have others as well. So for example, we can have ID3 that depends on entropy, I believe. So those are all basic algorithms. They will still do cuts or the decision boundaries based on like parallel to the axis. Yes, they cannot do diagonal, but that does not mean we cannot do diagonals. Yes. I'm still waiting for some response on the chat. So I hope you remember. So we wanted to have like diagonal, let's say. Yeah. So I'll just read out. I think Varun answered last time over email. So yes, like we could use some linear combination of uh, the input features. Yes. So if I had x1 and x2, we could use some linear combinations of those input feature to find diagonals. Yes. The only problem is decision tree does not, as a regular algorithm, it does not follow, and also linear combinations also could expand your search domain to a very large, right? So here x1 and x2, if this is continuous, I told you, right? So if it is categorical, we can easily split the data sets. So if the data set is of 100 rows, if I ask, okay, is this course difficult or easy? So based on whatever is difficult and whatever easy, the data set gets split into those many rows. All the difficult are here, all the easy are here. But the point is, if anybody wants to have diagonal, then that will come. But if we have, let's say, numbers, right? So if x1 varies from minus infinity to plus infinity, and x2 also varies from minus infinity to plus infinity, where do we take the threshold? Because splitting is easy in categorical features. Categorical means where the values are limited to a certain number of like countable set. But if it is uncountable, let's say minus infinity to plus infinity, what do we do? Yeah. So in this particular case, we have to choose all possible values as a potential threshold, right? Then that becomes also huge. Some of the parameters that help you are basically your own domain knowledge that helps you. Yeah. The second one is if we had linear combinations of those x1 and x2, that would again open up another set of parameters to choose from, which could be even higher, right? You could have many ways to combine those. Yes. So then again, you have to find which threshold works. Yes. So that's why to keep things easy and simple, decision boundaries parallel to access is fine. Decision boundary also works relatively okay unless you absolutely require some non-linear boundaries. Yes. Fine. So with that, that was the first question. The second question was what was decision tree's inductive bias, right? Uh, any guesses on that? Like what could be decision tree's inductive bias? It is the assumption, regardless of the data set, that the decision tree itself takes some assumptions about the data, right? Data or the model itself has that kind of bias, yes? Because linear regression, I am what I am, logistic says I can put just one hyperplane to separate, yes? That's logistic regression. So what will be decision tree? Hmm. Any guesses on, at least on WebEx? Okay. I've not received anything yet, but I hope you have thought about something. So decision tree basically assumes that if I build a decision tree, right? So it assumes that if I keep on asking questions on features, I will immediately reach to an example, right? Regardless of what the data is. Decision tree assumes that if I keep on asking questions, I will reach to an example. Yes. Uh, and if I do not ask any questions, that means, or if I ask less questions, I will get a very vague answer. Yes. So this specifically becomes an inductive bias of decision tree in terms of how do you control, right? The height of the decision tree itself controls the bias I have towards IGK. No need to worry. It's okay. The height of the tree is basically tells you the assumption that I have against the like the data set that I have. So if I keep on asking too many questions, I will reach towards the end, towards the leaf, and that will point me to a particular example. And if I ask less examples, that means I am at, let's say, level 1 or level 2, if you can see the slides, then I'm asking too many less questions, right? I will never reach an example with that. So that it basically says that if I ask too many questions, I will reach an example. If I ask too less questions, I'll be very vague. So if I ask too many questions and I reach an example, that means I'm memorizing. Whatever answer I will give you, I will particularly pick one example and I will give you that answer in decision tree, right? But if I ask only one or two questions or very less questions, I will give you a very vague answer, which will be more in terms of, and if I'm always correct, let's say I'm a decision tree. You asked me a question and I'm giving you an answer. Okay, true, false, randomly, let's say. That means I'm always true without even asking the question, without even looking at the data, right? I did not even look at the data. I'm just giving you a random answer. This is very similar to the inductive bias class. I hope you have recall. We have like oracle. Doesn't matter what the note was, I'm giving you the correct answer. The other one is memorization, right? Very far end. That means I will exactly look at the note and I will give you the answer. So here in decision tree, it's just the up way around. If I just ask few questions, I am the oracle. Just by looking at few questions, I can give you the answer. Or if I have to go till the end and then I have to give you an answer. That means I have asked a lot of questions while coming down the decision tree. Then I have to give you an answer. That means I'm pulling one example from the input and giving you the answer, right? So on the top lies oracle, on the bottom lies memorization. And anything in the middle will be generalization. That means in the decision tree, height should not be very large, height should not be too small. Height is too large is memorization, height small is oracle, right? Something in the middle is what generalization we want, right? I hope you remember inductive bias and generalization. And generalization is what we expect. We don't want to basically reach towards an exact solution, right? Exact example or exact input. So in the decision tree, inductive bias is the like the parameter, like the let's say assumption that if I keep on asking questions, I will reach to an example. Fine. So now, and this particular how many number of questions is controlled by the height of the tree. I hope you are okay with this. So if I cut the tree at level 3, right? So let's say level 1, level 2, and level 3 are the only thing I have in decision tree. Can I ever reach an example? Very difficult. I will have vague examples, right? I will have some combinations of input. I'll never reach an example. So if I cut at let's say level 3, I will get a decision tree which is generalized, does not memorize, or does not give super vague and like super correct answers flowing like oracle, which does not depend upon the data set itself. So that will be the inductive bias, the height of the tree, let's say. Yes, height of the tree controls the inductive bias. Yes, if you have a parameter that controls the inductive bias, that is called hyperparameter, right? I told you, like for example, if there's a function fwb, that means the function is parameterized by the weights and bias. But if there is some other parameter that is not parameterized through the data, rather we parameterize on separate stuff, that will be called a hyperparameter. Here the hyperparameter is the height of the tree. The height of the tree allows, basically if I increase, it allows me to memorize. If I decrease, it allows me to generalize, right? So that's why it's called hyperparameter. This is under our control. We control the inductive bias of decision tree by the height. That's why height becomes the hyperparameter here that we control. Okay. And as you go, every model, I think I have told linear regression, like logistic regression, this particular tuning hyperparameter will help you. Yes, going. We'll discuss as and when we go to the next one. So that's the decision tree inductive bias. Yes, these are the two questions I had asked last week. Let's go ahead. So just to give a background report, today we are covering support vector machines. Just to, I hope you remember this particular graph. So all the blue ones are from one class, all the orange ones are from the other class. What we wanted to do is we wanted to find a line or a decision boundary that basically has the highest margin, right? That is equally separated from both of the classes. It will be same distance as from the blue, same distance from the orange, and it has to be maximum also. We can have something parallel also that can be same distance, but we wanted the maximum to be maximum as well as equal because we want the margin to be the distance boundary to be in the middle. Yes. So of course, like what is the assumption of support vector machine here? That means we assume that there can be a decision boundary that can separate these two classes. Yes. And here there is one more term called support vectors. The support vectors are basically, if you can look, I don't know, mouse is visible or not. If you see the dotted lines above the red line is the decision boundary. The dotted lines, one is up with the equal to 1 and there is one equal to -1. These dotted boundaries are basically support, the lines that go through the support vectors. Yes, the support vectors are basically, if you see those two blue dots, through which that dotted line goes through, and there is one orange dot through which the other dotted line goes through. These are the inputs, or let's say input points, which decide the decision boundary. If you look at it, all the blue dots that are there in the particular graph that do not belong to, that are not equal to those two dots. If I change their position, the blue dots, I can pick them and then push them very far away. Will the decision boundary change? Will not change, right? Because this line only depends on this line, this dotted line, and this dotted line, and these points are closest to each other from separate classes, right? That's why, but if you change, let's say for example, there is an orange dot here. If I bring one orange dot from the bottom and I bring to the up, now do you think the decision boundary will change? It will change, right? Because now the support vector will lie on the new orange boundary. I'm hoping I'm making sense. If I put one orange dot in between the red line and the dotted line that passes through the orange, now what happens? Now the closest points to each other becomes not the older orange point, rather the new orange point that is in between, right? Now, if I have to choose a decision boundary that is equal distance from each other, decision boundary has to shift up a bit. Yes. So the decision boundary will change. The moment the support vectors change, the decision boundary will change. Right. That's why that's why those inputs are called support vectors, because the decision boundary is supported by those vectors. Yes. That means if there is any other orange point that is below that dotted line, we don't care. It will not change the support vector motion decision line. And if any other blue points are there that are up towards that line, that also won't change. Only thing that will change if the new support vectors come into play. Fine. So support vector machines are very robust to things which does not affect support vectors. If you get a new point which affects support vectors, then we are in trouble. Yeah. So now with this, of course, just to give a whatever we discussed last time. So we had these equations, right? These equations are for the top line. This is for the bottom line. I don't know if is the highlight visible? Can IGCAD just raise hand? I can see. Okay, highlight is visible. Excellent. Thanks. So that means if you see this one was the line equation for the top one, and where all the labels are +1, and this is the line equation for all the labels that are -1. Yes, and we wanted to minimize this one. That is equivalent to, if you look at the previous one, it is 2 over omega. That means we wanted the margin to be maximum. Minimizing W will give the maximum margin. Yes. And the constraint is derived, this yi multiplied by wxi minus b is greater than equal to 1. This is derived from the previous original SVM constraints. If you multiply these two, it will come up in that. So our final optimization goal is you have to minimize this w, like norm of w, and then subject it to this constraint. Right? This was the initial SVM. And it assumes that there exists a decision boundary which can separate all of them, because this constraint specifically mandates so. It says that if the label is 1, wx minus b has to be greater than 1. Okay, this constraint specifically says all the blue lines have to lie above it and all the orange lines have to lie below. So this is a very hard constraint, and this puts a pressure on SVM to find that decision boundary. Now the question comes, what if we have other issues to fill in? So one problem is, let's say we have a noisy data problem. Noisy data problem as in we have a decision boundary, but there is one point of the orange somewhere here in the blue areas. Then what happens? So that means, and it need not be that the data is actually like that. It could be also the fact that the data when got recorded, you recorded like a bad example, like it could be human error, it could be an actual input also, but majorly it could be a human error also. The second is, what if we don't have a linear separation? Here it's a super easy example. We have a line that is separating. What if we don't have a linear separator? Then what do we do? So today we'll be discussing these two portions of how can SVM or how can you modify SVM to handle these two cases. Yes, and of course it says like most of the data that we have follows this information, like as in like this happens very regularly than you can feel. So the first thing, let's go ahead. The two critical questions. I have a figure. Sorry, I forgot I had a figure. So the figures are here. Very. I hope it's visible. If you see, one on the one side there are all red points. On the right hand side there are blue points. But here, if you see, there are two red points here. Yes, and there are two blue points here. So that means there is a noise involved. Yes, this could not be actual data, but rather it's a very small noise. We can assume that there is a small line here that separates them pretty well. But because of that hard constant, that means everything below this has to be blue, everything above this has to be red. That constant will not satisfy. That means you can never optimize, you can never find those W and Bs with this. Yes, or you will find a minimize that will not help. Every time it will keep on reiterating, right? So if I ask a question to this, it will ask me, okay, you are at correct. I hope this is no. So if I have a decision boundary that is between the red and blue, the moment I ask a noisy thing, let's say red, right? So if I ask all, let's say all the blue ones are here. If I ask blue one, in optimization, what do? We basically ask, am I correct? If the decision boundary is here, blue, okay, you are fine. Another blue, you are also fine. Another blue, you are fine. Now it gets a red one. It will ask also a red one. Okay, red one, you are at wrong. So wrong meaning what? Now you optimize your W and B so that I am correct. It will try to move the line towards it, right? So that means by the time it reaches the best way to optimize this one would be I bring the line here. That means I will have to bring the line somewhere under the two red noise points. But then it will be again be wrong. I will ask other blues. Now there will be a blue on the top. I'll ask the blue. Blue will say, no, you are wrong. It will go up. So when you try to optimize this particular thing here, your line decision boundary will keep on alternating. It will start to go closer towards the noise, and then again it will start closer to the up noise. It will find the right one. It will find one. So optimizing that will be very, very hard. Yes. The second one that we have is what if there is no linear boundary, right? So that means here, for example, it's very difficult to draw a line that will basically put one on one side there will be blue, one side there will be red, right? I hope like that's super clear from this example. And both are like very known things. This is just, I think, summarization of the previous. So left one says this noisy data could be separated by a straight line, but then outlier will prevent the optimization. Yes, perfect separation and optimization. So we need some flexibility to handle the noise. Yes, that is one. Second one is what if we have a linear data? Decision boundary here is like a circle rather than a line. Yes, because we can draw a circle here to separate blue and red. And so the linear hyperplane cannot be solved. But SVM, remember SVM can only do hyperplanes. Yes. So what we need to do? We need to transfer it to higher dimensions to do it. We'll talk in how to do so. So the goal is to update SVM's algorithm, original algorithm, to adopt these two. Yes, noisy data and non-linear data. First, let's say handle the noise. Yes. Now, to extend this one, we have to introduce something called a hinge loss function. Yes, the hinge loss function looks like this. Given if you give it y and f of x, y is the one that is actual label. That means if it is red or blue is blue, and f of x is what the model predicted it to be. It is blue or red, and SVM predicts like -1 and 1. Okay. So here we say a max of 0, comma 1 minus yi wxi minus b. Yes, f of x is wx minus b or whatever we are planning. A hyperplane basically equation. Now the hinge loss is basically 0 if the constraints a and b satisfy, right? So a and b are the previous constraints of this one. So just to make sure, this constraint and this constraint, if they're satisfied, then your hinge loss will be 0, right? So 1 minus y f of x, the predicted is 1, the actual is 1, so 1 minus 1, fine. And otherwise, even if it is like 1 minus 0, if it is the other way around, it will just split over. Or otherwise, y is minus 1, f of x is minus 1, minus 1 multiplies, it becomes 1, so 1 minus 1 again becomes 0. So max again is always 0 if they satisfy, right? And if the data falls in the wrong side, then the function's value will be proportional to the distance from the decision boundary. Okay, that is our hinge loss. So, but this is a very nice function that is used also other places, but I hope you can remember. So hinge loss. And here, if you look at it, yeah, so interpretation is here. So y dot f of x1 is greater than equal to 1. There is no penalty uh, if we have correct classification. And y dot f of x is less than equal to 1. It gives you a linear penalty, increases with distance. There could be a question from your end that like why y dot f of x will be greater than equal to 1. So remember f of x just gives us the distance from the line. In SVM, we put a sign function before f of x to find out which label actually it is, like +1 or -1. Yes. So that's why y multiplied by f of x might also give greater than equal to 1. It will be exactly equal to 1 if it lies on the support vector line. Yes. Fine. So now, in addition to the like the original constraint, we add the hinge loss. So here, if you remember, what we had is this norm of W, right? The earlier one was like norm of W here. We wanted to minimize that. So in addition of this, I'll try to highlight, maybe, or sorry, I'm not able to highlight particular, but underneath. So minimizing norm of W. That is now updated with a new cost function, which has something called a like hinge loss. This, if you see, max of 0, 1 is same as the hinge loss that we defined. And it is summed over all the data points. Yes, that's what we have here. You can do the sum, you can take the mean of the sum as well. Both are fine. It depends on how much you want to prioritize. Mean also you can take, not an issue. So now we have two competing objectives, right? So once is we want to maximize the margin that is there, and we want to minimize the error. Fine. So minimizing the error, as in that means we have to make sure that whatever the points are here, they're either we are giving it some value. The hinge loss will give us some value based on its distance. And here, if you see this parameter there is another parameter called C here. And C is not decided by the data itself. It is decided by us once we run this model and we choose some values. So that's why it's a hyperparameter for the SVM. Now this particular hyperparameter C determines the trade-off between increasing the size of the decision boundary and ensuring that each X lies on the correct side. Fine. Uh, one example I want to give is, for example, let's say draw. Okay. So if I have this points here, let's say 2 points, fine. This one will just help you like a little bit better, maybe. Okay. So I have circular ones are from a different class and dots were a separate class. If I had to do SVM, this would be the highest margin point. Yes. But what if I had, let's say, these 2 points and I have a circle here and I have circle here and other circles are there. What would be the best decision boundary, right? So if I had to choose between the best decision boundary, if I have to exactly do the optimization, I have to choose something here. This is very nice, but this does not take into account that this might be a wrong input, right? So what we rather want is the decision boundary to be somewhere here, right? So that this can be ignored, this particular point, what is here, this should be like ignored. That ignorance can come from this hinge loss. That means, okay, some errors you can make, this is the cost you have to pay. But if you pay this cost, you can increase the W is the size from like say this to this, right? So the boundary, the margin boundary, so I can increase the W at the cost of making this particular error. but this one will help me putting the decision boundary at a correct place. If I have to make sure that I make no errors at all, I have to bring it here. But then the point is I have to reduce the W so little that I'm losing there. Yes. So that means this becomes a trade-off. So either I increase my margin boundary or I allow few losses. Right. This is what the cost function tries to do. I hope that is clear. And if we include this, include this, and the value of C here is chosen experimentally. Yes. And if the SVMs include this particular hinge loss in their cost function, that means we want to optimize such that this becomes minimum, then this becomes a soft margin SVM. Yes, soft margin support vector machine. That means a not, and the original formation is called hard margin SVM, right? So because it's a particularly pretty hard, that means uh, we are not basically making any errors. You find whatever is the perfect distance boundary. But this one, the current one that is here, that is soft margin because we're allowing one of the errors. Yes. Now what happens? So you can see like for sufficiently high values of C, the second term in the cost function, if the C increases very large, then the second term of this function will not matter, right? It becomes super negligible, right? But its importance doesn't matter. That means margin, like having maximum margin is what matters. Small losses, we don't care. So SVM will algorithm will try to find the highest margin by completely ignoring misclassification. Yes. Now, if we decrease the value of C, what happens? Then making classification errors. If you see, if you decrease the value of C, that means the width of or the size of the margin plays lower importance. Yes. So, but the right hand side, which is the hinge loss, which basically penalizes for every misclassification that we make, that becomes more important. That becomes more costly, and SVM algorithm will try to make less mistakes. Yes. So and that will come at a sacrifice of the margin size. So it will try to move it in between of this dot and the two classes. Yes. And of course, larger the margin, if it is larger the margin, it is more generalized because it assumes that okay, this might be probably, it does not exactly depend upon this particular example. Rather, it is like it assumes that you might have made some mistake here, most likely. Yeah? So that's why it wants to make sure that everything is correct uh, with this particular margin. But if this with this here, it's more generalized, and this with this here, it is more memorized. Yes. So here the C is the hyperparameter that tunes. Either I remember a lot, that means I have to make sure the training data, I don't make any mistakes in the training data. Or if I move it here, then it will assume that, okay, if there is a new dot point here, it makes no mistakes there. Yes. So this particular thing will not make any mistakes. Fine. So I hope this is clear, at least the parameter C. Just to revise, high C, second term dominance, algorithm tries to classify all the points correctly, may lead to overfitting. Overfitting will come back, but majorly leads with smaller margin. Low C, first term will dominate, yes. And then algorithm allows for some misclassification, then larger margin better for generalization, more robust to noise, yes. So what is the sweet spot? You have to pick generally middle values of C, right? Some values of C that are not very high, not very low. Yes. We'll come again how to choose a little bit more later. Sorry. Yeah. And now just to go back, so this problem is solved because we have chosen a margin now. Uh, now we have chosen this margin. Earlier in hard margin SVM, we were not allowed to choose because optimizing this would be very hard. But now, assume this is a straight line, we are allowed to do this because some misclassification is allowed. Yes. Now we jump to the second problem. Now second problem is nonlinear data, right? Now SVM also can be adapted where the data cannot be separated by a hyperplane in the original space. However, the point is if we can transform the original space to another space, most likely in higher dimensional space, where linear separation is possible, right? And we assume, of course, like if we transform into a high dimensional space, there might exist a hyperplane which can find a linear separation. Okay, that's the assumption here. And uh, key insight also, like as in many nonlinear problems in smaller dimensions, like they become linear in higher dimension. Okay? With this assumption, so what we can do is, one example is here, let's say dealing with nonlinear data. Fine. So here, if you see, it's possible to transform the left hand side to the right hand side. So what here we have done is basically transfer two-dimensional non-linear separable data into a linear separable high-dimensional data. This particular uses a specific mapping. That means every x in the previous dimension has been modified, has been transformed to a different dimension in like the high dimensional space. So x becomes transferred with, let's say, phi of x. Let's say that is a transformation. Let's say phi be the transformation. So phi I have used here. So for example, here if an input point is q comma p, I could apply like a function here, yes, which will take just the q comma p and then make it a, like a quadratic. Q square is 2 root 2p and p square, and becomes a, like a 3D point. Yes. With that transformation, if you see now, all the blue points are closer here, all the red points have gone up. Now, if you see, I can definitely draw a hyperplane. Fine. In this, the hyperplane, like the plane would have been just a line, maybe here it is line because it's a two-dimensional space. But at this case, it becomes a 3D, so the decision boundary will be a hyperplane, like a plane here, for example, and the plane can cut somewhere in between of like the blue and the red, right? So the moment we transfer to high dimensional space, we assumption, of course, is like we can get a hyperplane that can cut. Now remember this hyperplane, if we do a cut, it does the linear separability in the higher dimension, right? But to find the actual, like when we go back to training and all that's like testing and all that evaluation, we again have to drop back to the older dimensional space because the data will come in older dimensional space. Again, transform and then ask question. Yes. But the problem here is like, how do we know, like which mapping will work? Here, though, I have given you like if you can map it qp with q square, it will do this. But how will you know? There are like infinitely many transformations available, right? Uh, so how do we do? So one of the ways is like just keep on doing many. That's computationally expensive. Cannot do. Yes, there are just too many mappings. One way we can do is like God bless the scientists. Yes, so they came up with something called a kernel functions. Yes, or we can call it kernels. This is very popular regardless. So what we can do is we can use kernel functions to work in high dimensional space, but we don't have to do the transformation explicitly. Yes. Now to understand how this is done, so I've just written a summary here. So we can work in high dimensional space without explicit transformation. I will come back to those two things in some moment. Yes. So the original equation here. So if I have this, okay, so if that my optimization problem is minimizing like the margin, that is still remains, where we are subjected to this constant. That means anything above the line is a different class, anything below the line is a different class. We are following still that thing. If we extend it to and we find the Lagrange multipliers transformation, we do a dual transformation. Basically the original problems behaves like this, right? So max of alpha I, Lagrange multipliers are all these alpha terms, they have particular constraints, but we can do this transformation, right? So, and the most important thing that you have to look at is the max of alpha is there, and then minus half of two summations, like summation over summation, then yi alpha I. But if you see, there is a xi multiplied by xk. Fine. So this particular thing, like xi multiplied by xk, is a dot product that we do in the original space. If you look at this, we have done the dual transformation of this optimization problem to this, right? This is still in the original space. Our goal was to, and we still cannot find a linear separation in this dimension, right? What we need to do is we need to move the x of I to a different dimension from 2D to, let's say, 3D. We have to use the function psi, let's say, or phi function to move one blue point in the two-dimensional space to a three-dimensional space. That's for an example. But for here, xi has to move to, let's say, phi of xi, and xk has to move to phi of xk. Yes. Uh, and then if we do the transformation and then apply, then try to optimize this one, then we can probably get a linear separable, but in the high dimensional space. I hope this is clear. So this particular thing is the dual transfer Lagrange, like multiplier transformation or dual transformation, you can tell, of the original problem. Here xi and xk are in the original dimension, but our goal was that in this particular original dimension there was no line to be found. Rather, if we move them to a high dimensional, there may be a line that separates. Now here, if you see, the only place where the xi and xk are required are this dot product, xi dot xk. What we have to do is we have to transfer this xi and xk to a high dimensional space and then do the dot products, right? And then we can optimize this particular thing and we can find that all the alpha is probably that will give us the hyperplane. So what we can do is we can take the individual vectors xi and xk, like through the entire equation, through the optimization. We can do the transformation. That means we can apply the phi of xi and then phi of xk. We can move them to individual vector. We can change xi to phi of xi and then do the dot product. Yes. Now what happens? So if we want to do this transformation into high dimensional, we need to transfer like xi to phi of xi and xk into phi of xk, and then multiply phi of xi with phi of xj. Now that will be very expensive, right? Every vector has to be transferred to high dimensional space, and then the multiplication, the dot product, has to happen in the high dimensional space, which can be super expensive. The other way around is the, like, because you have to understand that we don't care if the transformation takes place where. We are only interested in what is the value of xi multiplied by value of xk. Fine. This is the only goal we have. I hope we're clear. So we don't care how xi dot xk is calculated. Rather, we are only interested in what is the value of xi dot xk. So instead of individually transforming xi to xk, when phi of xi and phi of xk and then doing dot product, we can use the kernel trick. Okay. So here we can get rid of the costly transformation of the original feature vectors into the high dimensional feature vectors, and we can avoid their computation in high dimensional space. Rather, what we can do is we can use a simple operation that first calculates their, let's say, dot product. It could be dot product, it could be something else also. Dot product of those two individual vectors. So first we'll calculate dot product of individual vectors and then apply the transformation. Fine. So this is the kernel trick. So here what we have to do is we don't have to do the individual transformation, as well as we don't have to do the operation in high dimensional space. So we are saving both the things. Here on the left hand side of the kernel trick, if you see, we are doing the operation in the low dimensional space, and whatever the value is, that we are doing a transformation to a high dimensional space. Fine. And then once we find the value, we can just replace it in the place of xi dot xk, this particular value. Okay. Oh, sorry. And so there are few examples that are available in the world that do this kernel trick. Not all the functions, of course, will have the privilege to happen this way. One of the examples, like linear kernel, is there. There is a polynomial kernel. Polynomial kernel is super famous. Yes, very useful. And the other formulation is like quadratic example. This is, I will just explain that in a little bit more depth. So for example, here you remember that only thing that we read is xi dot xk, right? And after we transform, we require phi of xi dot phi of xk. Okay, that is the only thing that we need to remember. So here if you assume original vectors, let's say they are q1 and p1 and q2 and p2, q2 and p2, yes. Here what we can do is if we go through the top path, we can individually transform the vectors. So here now q1 p1 becomes q1 square root over 2 q1 p1 p1 square. Similarly for q2 and p2, right? And then we can do a dot product. Dot product will be multiplying these two vectors, yes. Sorry, I'm not able to select properly here, but I'm assuming like q1 square comma root 2 p1 q1 p1 square multiplied by its equivalent q2 and p2 square, right? We have to multiply in high dimension. Yes, we can do that. Or otherwise, what quadratic kernel says that what you can do is initially you can do a dot product. You can do q1 p1 my dot product q2 p2. That means it becomes q1 q2 plus p1 p2. That is what it's here, simple operation. And then you can do a square. Fine. So here, how much did we save? We did not convert individually into like high dimensional space. Also, we did not multiply in high dimensional space, right? So this is like a very fancy quadratic kernel technique that we use uh, to resolve this issue, right? And there is one more popular also like Gaussian kernel, also called RBF. And most likely when you do SVM and you want to do non-linear classification or non-linear SVMs, you will generally end up using RBF. Yes. So here basically what it says that what we can do is we can have in the Gaussian formula. So, and xi x minus x prime is basically the Euclidean distance between two vectors, yeah, x and x prime. It could be like xi xk, that is the same thing. Yes. And this distance also you can have many variations of this distance. Yes. Uh, and RBF's full form is radial basis function. Yes, just to have. And what this transforms it, if you do this expansion of this e to the power this much, this will become an infinite dimensional space. Yes. Remember, this one transforms into linear kernel, same, but just a transformation. Polynomial kernel D is the space, quadratic kernel does the square, yes, quadratic space. If you do RBF transformation, it takes one point and pushes it into an infinite dimensional space. Yes. And we assume that in the infinite dimensional space, there will be a line that can cut. Yes. And I will show you a little bit, probably if there is time or next class in the beginning. So here, if you see, what I can have is based on the sigma. If I change the sigma, these are my Gaussian kernel will vary. I'll show you example how it exactly shows, not super close, but yeah. So if you vary the sigma, if you see the small sigma will result in curvy and complex boundaries, high variance for now ignored. But if I choose large sigma, then it will be smooth and simple boundaries. Yes, that basically the sigma. If you choose that way, it decides like the variance in the Gaussian curve that we will have. Like the distance will be, it will be like a very straightforward, like pointy like Gaussian curve or very flat Gaussian curve, right? That's what sigma decides. And if you keep on varying them, you can choose what kind of that Gaussian curve at particular distance is. And how do you do final prediction then? So remember, so what we did is we still had this optimization problem in original dimension space. We moved to its dual transformation where we had to do xi dot xk. Now, instead of transforming individually through phi function, what we did is we first did the operation and then did the transformation, which saved us time and computational power, but way faster also. Now, after that we still come back to the same equation that we still have to apply the sign to get the final output. Fine. This kernel functions that kxi and xk, that kernel function varies. That kernel function could be your RBF, could be your quadratic, could be your polynomial kernel, could be linear, or if there is any other kernel available in this world that follows this principle, sure, we can use them. And of course, like support vectors are what? They're the training points with alpha I greater than 0. Only these, because if you will look at this particular equation, here, the alpha I and yi is equal to 0 and alpha is greater than 0. Only where alpha I will be greater than 0, those are the only points which will matter in creating the hyperplane, right? All other points alpha I should be 0, because if they have some alpha I value, then they add to constants, but that will not happen, right? That's what it says, that the decision boundary has to only depend upon support vectors. And generally we have we don't have support vectors generally are small compared to the rest of the training data set, because those are the things that we want to find out the minimum distance. So eventually, even if this looks like once you do the dual transformation, there might be a lot of alpha i's, but eventually most of the alpha i's are 0. So you don't need to optimize. The constraints will be minimalized to those support vectors only, right? So that means for every alpha I is equal to 0, there will not be many alpha i's, because most of the alpha i's will be 0 because they are not support vectors. So eventually you will end up with few constraints. So this will be again faster optimizing this one. And so just a summary, so we have support vector machines. We can have that there were two problems. One is dealing with the noisy data set, other with nonlinear. The one way to solve the noisy data set was using the hinge loss, which uses and also adding an hyperparameter which decides the trade-off between those either maximum margin or allowing few mistakes. So higher C, more complex model, simpler model, we'll come back to that. Then kernel choice is there we can do that for the nonlinear boundaries. We make them to higher dimensional space. Then, but how we choose to higher dimensional space, that is decided by kernel. We can have linear, polynomial, and RBF, and RBF's like sigma that controls how smooth the decision boundary is, and cross validation that will come. Yes. I will show you the code, but probably not today, as there are a bunch of graphs that are there. So I'll just summarize with limitations and strengths today. But next class in the beginning, I will go through the code again. And SVM again, there are strengths to it. They're very effective hand dimensions. They're very memory efficient, because I told you, doesn't matter how many alpha i's are there, most of them will be 0, because our alpha I only for support vectors will have values greater than or equal to 0. And versatile, because different you can try same algorithm SVM, but you can transform to many other high dimensional spaces. The way you transform will differ. So it can have like RBF, linear, quadratic, or if something else is there, sure. And it works well also with smaller data sets, not an issue. Limitations, like if the number of features increases too much, there might be a little bit tricky scenario that can come. And also large data sets, because you still have to calculate distance between every 2 points. If you see xi minus x prime for the RBF, that means for every 2 points I have to calculate this Euclidean distance. That means becomes n square. If 1 million points are there, I'll have to do 1 million square times calculation of distances. That's super expensive. And which kernel to choose, which parameters to choose can be super tricky. Yes. So generally, if you have medium-sized data sets, but decision boundaries are not very simple or linear or something, like God bless SVM. Yes. So the only thing remaining is the implementation. I will show you the graphs on Wednesday first half, and then we'll cover the next algorithm that is there. Yes. Okay, that's it for today. I hope SVM is clear. Yes. If there are any questions, I'm here for 2 more minutes. And yes, please find a partner for projects, those who are into credits. Those who are also doing audit of this course, if you want to participate in projects, please feel free. Exams grading will be our choice based on how many students are actually doing credit. If it's just too much, we'll try to avoid. But projects, you can participate, not an issue. It will be a pleasure to look at all your projects, not an issue. And Friday is the deadline. Friday, there is no class, but deadline is there. Keep everything ready. You can anyway submit it Wednesday. You don't have to wait till September 5th. Okay, there are no more questions for today. So on Wednesday, we'll discuss the coding for SVM. I'll just show you a few graphs how this kernels and things behave, and then we'll finish the last fundamental algorithm in supervised. Okay, bye all.